Thank you very much for kind introduction, and thank you very much for having me. So today I would like to talk about this building control problem and what can we do about it using physics constraint deep learning. Basically, like we have this problem with energy efficiency, and buildings generate loads of greenhouse gas emissions, almost 20%. And one of the contributing factors are energy inefficient building controls. And this is due to the fact because they are classically designed and tuned and deployed by hand by experts in the field. But in the last decades, one of the promising research approach has been to use advanced control strategies such as model predictive control to mitigate this problem. But model predictive control has been classically designed and developed in the process control industries and never since emerged in high performance safety critical applications like automotive, aerospace, or high performance robotics. But even in these setups where the margins for gains are pretty high, 95% of the control loops are simple PID controllers, and only the rest is model predictive control, which is there for safety and performance. The reason is deployment and design of these highly complex control strategies is very costly. So you can think of this relationship with PID controllers on simple, low level, and model predictive control on high level, complex predictive, as like this kind of analogy when, as Morpheus was guiding Neo to fight the bad guys, like model predictive control is supervising PID loops to track the reference and do the disturbance rejection. And the whole optimization of the system level wide is done on this model predictive control side. So what do we think of model predictive control? We formulated as this following optimal control problem, where you have some performance objective, be it reference tracking or energy minimization, and you want to find the optimal trajectories of your control actions subject to the constraints of your system dynamics model, which is typically designed by hand from first principles or obtained by system identification, and constraints on your state trajectories and input trajectories. And how do we implement and solve these problems in practice is that we formulate constraint optimization problem and use constraint optimization solvers in real time. So we measure the state of the system, we solve the constraint optimization problem, we deploy the computed control actions, and in next time step, we redo the same again, like we recompute the problem. So you can imagine this procedure is quite computationally heavy, and that's why it's being used only on the safety critical and high performance tasks. But buildings are a little bit different, right? Like every building is different, and by optimizing them, we need to design these specific control strategies one by one. So what happens when we actually do design and deploy these highly complex control strategies in a real world building? This is a particular example of field deployment in office building in Belgium. Well, very nice things can happen. We can save energy a lot. Like we save almost 50% of energy and 40% of the comfort improvement over the period of several months. On the right-hand side, this kind of comparison of the performance when the green dots are the model predictive control, red dots is classical rule-based control tuned by hand. And basically on the top figure, the lower is better, and on the bottom figure, the left is better. So you can see this huge improvement in performance. So why this happened? Some intuition can be gained by comparing the trajectories of the system dynamics, where the top figures are trajectories governed by rule-based controller, and the bottom figure are trajectories governed by this complex model predictive controller, where first figure is our trajectories of these temperatures within building, which we want to control to maintain desired level of comfort. And bottom figure is this trajectory of the ambient temperature is something what acts against us. And in the middle, we have these supply return temperatures, which represent our control decisions. So you can see like under rule-based controller, these control decisions are pretty static. They don't vary much with variations in the ambient temperature or with the state of the dynamics of the building. While the story is very different under model predictive control governments, like these control actions are highly dynamic because they adapt to different scenarios. They take into consideration time of the day, desired comfort, and future forecast of the ambient temperature, weather forecast, and basically estimate of the internal energy in the building. So that's why we gain so much, because decision complex is far more complex than simple rules. But there is a catch. The design and implementation of these highly complex control strategies is really tedious and costly, and can take up several months of design. To give you some intuition, I will guide you through some steps, high-level steps of this design strategy. With this real-world building, you first need to understand the physics, to understand what's going on in there with those engineering systems. So you need to have some design experts to help you make sense of it. And then in the modeling and simulation steps, we design these high fidelity digital twins, basically. Like, people use domain specific languages like energy plus Transys. We use Modelica in this case. Then we obtain this control oriented model for design of the model pretty controller, and only then we applied this strategy in real time. And after this, we still need to do some manual tuning based on the performance in the real world. Basically, this design, modeling, tuning, calibration took us several months to have like this field test deployment. So you can imagine like this highly complex process is the main contributing factor why we don't see this widespread adoption of these high performing controllers in practice in building, because you would need to repeat this process all over again for a new building. So we asked the question, can we use better with machine learning strategies like deep learning and with embedded physics constraints? So we believe like we can do far better with the method we call differential predictive control, which allows us to take the principal physical equations, which are agnostic of the building and physical system, and learn only the unknown parameters of the physical dynamics. And then from learning this system dynamics model, we can learn constraint control policies only from observation of the data. So the methodology is as follows. We observe the behavior of the system for a time period. We learn this physics constraint neural state space model, which is now basically represented by structured constraint neural networks. It's fully differentiable. That's why we can use it as a part of the closed loop dynamic system with neural control policy, and used designed model predicting control loss function, which allows us to optimize this neural network allowed by differentiation. And we can simulate this offline over the distribution of desired scenarios, references, disturbances, and potential scenarios which may happen in the real world. So what happens when we use the real world data set to train the system dynamics? How do we do? We can do pretty good. We can learn from really small data sets. In this case, we use only 10 days for training data, shown on the grayed area on the left. And we have been able to generalize on open loop simulation trajectories on the following 20 days. And we compare like side by side with the real measurements from the real building. So the red is the ground truth and the blue are our predictions. So we have been able to achieve state-of-the-art performance by improving the accuracy of the classical system identification methods in the literature by almost 50%. And the bottom line here is that by combining physics with expressive power of deep learning allows us to learn highly accurate, generalizable surrogate models for this building dynamics without the need of like months of development time and manual tuning. Like we can do this in days instead of months. So then how do we do in controls, in closed loop control? This is another example using simulation case study of the 6-zone building, where on the left-hand side, we have again these trajectories of the zone temperatures, which should remain within the prescribed bounds given by dash black. And on the right-hand side, we have these mass flows, which are manipulated variables, which again needs to satisfy constraints. And we have been able to synthesize the suboptimal control behavior purely based on this offline simulation. So the bottom line here is that we don't need, again, like the physics-based models to have these high performance controllers. how can we do in kind of more real-world setting with controls when considering limited computational devices and go on edge, right? So in this case, we consider this Raspberry Pi microcontroller and compared this differential operating control side by side with classical explicit mode operating control. And not only we observe that we are much more efficient in scalability, computational and memory efficiency, but we even outperform this classical approach in performance task on reference tracking and constraint satisfaction, because basically our neural network was more expressive than classical control. In this case, is explicit MPC. In conclusion, I have presented this generic data-driven modeling method for building thermodynamics based on physics-constrained neural state space models, which allows us to learn constraint control policies from time series data using this differential operating control strategy. And both approaches are physically interpretable, they are constrained, they are sampling efficient. And this brings us promise of reducing the development time from the classical approaches from months to days using these data-driven approaches. So our future work is focusing on real-world deployment, scalability, much larger systems, and doing progress on theoretical side, doing some theoretical guarantees on constraint satisfaction and stability. So if you are interested in more technical details, please feel free to reach out to us, read our papers, or you can visit our GitHub page where we are developing this constraint optimization package in PyTorch, particularly tailored for solving this modeling and optimal control problems. So here I would like to thank you very much for your attention.
Thank you very much, Jan. And it was great from your group that you put directly the GitHub link in the slides so that you avoid the question about open sourcing your code and similar stuff. So first question is, when should you prefer a classical model-based control, optimal control, instead of your approach? Is there any specific application where let's say the classical approach can outperform or give guarantees that your approach cannot?
Yeah, this is an excellent question. So I would say like almost everywhere where you can afford it, right? So when you can afford, definitely go for model-based controls because it will give you guarantees, and it has like decades of the development theoretically and practically. So our approach is like fairly experimental, is new line of research. So we don't have yet like this hardcore mathematical guarantees on all of this behavior. Everything what I presented was empirical. But when you don't have like the resources to design and deploy your model-based operating control, like in buildings, and life is not at stake when the controller fails. Like in this case, like for this kind of situation, that's why we are developing these data-driven approaches.
Good. So maybe it is not worth using them for like a spacecraft because it would be too dangerous. But
I wouldn't go for that right at this stage. That's why we are focusing on these type of applications right now.
Very good answer. Thank you very much. So there are lots of questions and lots of compliments for you from the audience. So great talk again. And Emilio from the EPFL is asking, how many parameters did the deep neural network have? To me, it's surprising that only 10 days worth of data were enough to train it well. Well, what was the granularity of the data?
We had, I believe, like 1,000 data points for this 10 days. So I believe it was 15 minutes sampling time, if I remember correctly. And explicit number of parameters, I don't remember exactly. It was in the number of tens of thousands. So it was not super huge model, but it was not small model. Like when you have like this linear state space model, they have only hundreds of parameters, right? So we had like more expressive capacity, but the main gain was in this physics informed structure because we didn't use like these vanilla neural networks. We basically kind of build this digital causal twin of the building model, right? So all the causal relations which we know are there and are agnostic of the building be implemented, right? So like there's these convective heat flow equations, which we don't know the parameters, but we know that the physics holds, right? We know, like, for instance, that buildings are dissipative systems, so we can constrain eigenvalues of these neural networks to be dissipative. And these kind of basically physical insights are allowing us to learn from much smaller data sets because we are constraining them to behave in a certain way already by design.
Cool, very cool answer. And also a couple of more questions about how did you consider physical constraints in the machine learning model. One question is, can the physical constraints be interpreted as strong priors? So maybe if you could elaborate a little bit more on how to include the physical equations, the prior knowledge into the machine learning model, and how much robustness can this approach deliver?
Yeah, this is a great question. So I will first answer the question of how can we incorporate these equations. So basically, we are using PyTorch, which is highly modular and very flexible for, like, writing down your math. And when you have differential model, you can construct the computational graph. And it doesn't have to be neural network. It can be computational graph of your physical equations. And now you can blend them together with neural nets. So this is technically how we do it. We also use, like, the penalty constraints to in the loss functions to incorporate inequality constraints. And then we are using structured linear algebra to replace classical weights in your neural network with more structured alternatives, which allows us to do eigenvalue constraints, sparse system identification, and this type of kind of priors, which may be good for your application. On the robustness side, this is kind of very good question, right? Like, because when you, for instance, use these penalty constraints, they are soft constraints, so they are not hard constraints. So, but they are also already, like, in machine learning community methods which emerge, which are there to solve the hard constraints. And I kind of encourage people to go and visit the Priya Donti's keynote, because she will be surely talking about some of those methods using, like, implicit layers, which can give you more robustness and guarantees if you really need it. So basically, you could use these type of implicit layers in conjunction with this approach what I just presented to give more robustness if you want to have more kind of guarantees on performance.